Welcome to Partial F-Test, testing the significance of a subset of variables. We have tested for one specific named coefficient using the t-test. We have tested for the overall model, which includes all the slopes, and we used an F-test. Now what happens if we have more than one, but not everybody? Hey, we got a test for that. It's called a partial F-test. A partial F-test is where we want to look at a subset of X variables, but not all of them, but more than one. It's an F-test. P-value, 6 steps. There's an HO and an HA. We'll talk about the HO and the HA, and we'll talk about the calculation of the partial F stat, which has a little bit of labor involved in the calculation of the F stat here, but nothing crazy, okay? So often you see a partial F when we want to test that selection of dummy variables, because really when we brought in those dummy variables, what were we doing? What was our goal? Our goal was to see does the quarter that you're in matter? Well, that's kind of like the question. Now, we brought in 3 dummy variables and had a base case, and so there's 3 variables that we bring in the model, but they really all represent one concept. Does it matter which quarter you're in? Does the quarter that you happen to be in impact sales? Is sales different from one quarter to the other quarter on average? That's the fundamental question. So really, when we bring in one quarterly dummy, we bring them all in, right? Woohoo! It's the whole party. So it makes sense that if we're going to evaluate with, are sales different in one quarter versus another, that we test the entire set of quarterly dummy variables, not one at a time, because that introduces some other problems, all together. And so when we test them all together, we end up we have a sort of a comparison of 2 different models. We have the full model and we have the reduced model. And
one of these things
they're different.
Is not like the others. One of these things doesn't belong. Can you tell which thing is not like the other by the time I finish this song?
And who doesn't belong? The quarterly dummies. So we're going to have a model with all the quarterly dummies in it. We're going to have a model without the quarterly dummies in it. We're going to compare the 2 models, see which one's better. Or whether there's a difference between the 2 models and how well they explain, in this case, sales or whatever the dependent variable is. So we have our full model. Has everybody in it. Every single variable is in there. And then we have our reduced model. Right? So here's the quarterly dummies. Quarterly 1, quarter 2, quarter 3, quarter 4 must be the base case. And then we have advertising in the same month, advertising the previous month, thinking being perhaps there's a lag. You see an ad, then you kind of, you think about it a little bit, and then you act on it. Okay, and we're selling houses. Okay, so and then we have mortgage rate in the previous period, clearly before you decide to buy the house, it's the mortgage rate, and then housing starts. Kind of an indication of supply. If a lot of new houses coming on the market, maybe you'd be more inclined to buy. And then we have the reduced model. No quarterly dummies. Everybody else is still there, right? Just no quarterly dummies in there. Okay. So it's not too hard, right? We still have our 2 models. So let's look at our 2 models. And background. We see our adjusted R squared. 78% of the variation in housing sales, explained by this model. Not bad. Is the model significant? Yeah. Pretty small p-value over there. Model significant. Any of the variables individually Not significant? Ooh, X4. X4. Advertising in the same period doesn't appear to be significantly different than 0. Advertising in the previous period, ooh, tricky one. Depends on how you chose alpha. Depends on your balance of type 1, type 2 error here. So, interesting there. But it looks like a mortgage rate is a significant factor. That's not surprising. Interest rates go up, housing sales go down. And it does look like housing starts, an increase in housing starts increases sales. Just more stock, just more supply out there can in some ways can drive demand as well. Okay, so some interesting results there. So there's our model. There's everybody in. Now we're going to zero in on a couple of items in this model. So, and you'll see the formula in a sec. A couple of the key components is R squared. Ooh. Some of the key players in this, R squared. Look for it to appear in subsequent episodes. Another key players is this sum of squares, this SS stuff. Sum of squares. Spoiler alert, they show up again. They play a pivotal, yeah. God, they play an important role. My goodness. I'm in a speaking business, eh? You'd never know it. Okay, so they play a very important role again, because sum of squares of the regression is how much of the variability, it's a kind of a stand-in for how much of the variability we're able to explain, and the sum of squared residuals, the variability we can't explain. Those will be important to us. So we have result, full model. Do we do it again? Right? Another regression result, nothing special, just do another regression, except don't put in the dummy variables. Key player again was we're going to compare the R squared. I mean, essentially what we're going to look at is do we get a real big drop in R squared? If R squared will either stay the same or likely go down, right? And we saw that when we were talking about multiple linear regression. Even the inclusion of silly variables won't reduce R squared and will likely increase R squared. So R squared is expected to go down. Not a big deal, not a surprise. Did it go down by a lot? That's the key question we ask ourselves. Did it go down by a lot? And by a lot, we'll couch that in the words of a statistically significant amount. Okay. Also, is the sum of squares that we're able to explain go down a lot? It's by extension, because all these items were used to calculate R squared. So they're all related to each other anyhow. Okay, and then, or did the sum of squared errors go up by a lot? Because remember, what we're not able to explain shows up in error. Okay, that's an important result. Now, interesting. Look at the sum of squares total. Look at that number. Look at that number. Look at that number. Look at that number. It's the same. The same. So, whatever doesn't show up in what we can't explain, honest to goodness, does show up in the part where we can't explain. Now, was that a significant shift? Was that a big shift? Don't know yet, right? We have to run the statistical test. And as with every statistical test, there are 6 wonderful steps. That's start with step number 1. We'll talk it through. Okay, so let's start step number 1. Now, generically, step number 1 is just that the betas, whichever betas they are. Now, in this case, they were the first three coefficients in the full model. So that'll mean we'll look at beta 1 is beta 2 equals beta 3 is equal to 0. Let's get the paper up here. Looks like we're going to have to start writing some stuff down here. Okay, so we keep track of the full model, which had 7 predictors. Reduced model had 4. And so we have 3 extra predictors, which means there are 3 variables that we've eliminated from this model. Okay, 3 coefficients are on the clock, are being tested. been eliminated to see whether they matter or not. If they don't matter, they're going to get voted off the island. Which 3? That matters. Now, it just happens in this case, it's the first 3. But that it does not have to be the first 3. It could be different than the first 3. Okay? So that's important. And so we're testing is beta 1, beta 2 equals to beta 3. That they're all equal to 0. Every single one, worst betas in the world. Or versus at least 1 beta I doesn't equal to 0, where I equals to 1, a 2, or a 3. And there's our HO, there's our HA. Step 2, as normal, let's say it's just whatever alpha, 0.01, just to start this off. See how that goes. Okay. Step 3, hey, now we're going to calculate the F-stat. And that's the important next steps. All right. So there it is in nice, clean language. Now, remember, it's the variables that are being tested. Okay, so what's going on when we test this? Just some introduction into how the F-test works. We'll get into the calculation, but it's good to know how it works. So we have an amount of the variability that we're able to explain, right? And that just comes out of the output, and it's there in red. It's a big honking number. Okay? And that's from the full model. Then when we reduce the model, it does go down. It inevitably will go down. And so we're trying to now determine whether it goes down by a lot. Or in Statsi's language, did it go down by a significant amount? So we're comparing those two numbers. One way to do the F-test, compare those two numbers. Okay. And did they drop by a lot? So we have SSR full, SSR reduced, lost a little bit. How much? Notice the SST did not change, right? So we calculate that change and we get a number. Okay, cool. Okay. And we divide that particular number by the degrees of freedom in the numerator, right? Remember the F statistic at its core is just the ratio of two chi-squared statistics. One is the variability of what we are able to explain relative to the variability that we're not able to explain. Doesn't change here, okay? Still an F-test after all. Now, what are the degrees of freedom? Well, it's the number of little betas you have in your HO, right? No different than with the F statistic stuff we did for the overall model. Count how many betas you're testing. That's how many degrees of freedom you have in the numerator. It's not more complicated than that. So that's the same. That's a fundamental part of the F-stat itself. Okay. Now, we have the denominator. SSE, amount of variability we're not able to explain. And then its degrees of freedom of n minus p minus 1. Okay. And so we have the MSE from the full model, right? Take the SSE from the full model, boom, n minus p minus 1, and you get that result. Now, it's kind of nice. We don't worry about the MSE for the reduced model, by the way. So that doesn't come into the formulas at all. So you'll notice that it is missing here because it's not important. Okay. We're comparing our reduction in what we can explain relative to what we couldn't explain in the full model. That's so just as a sidebar on that. The degrees of freedom, again, the numerator degrees of freedom, because we remember that every F-stat has two numbers that define its degrees of freedom, a numerator degrees of freedom and a denominator degrees of freedom. The numerator degrees of freedom is the number of variables being tested or the number of variables being eliminated. Okay, P minus Q if that's really, you want to make it more confusing for yourself. P being the number of variables in the full model, Q being the number of variables in the reduced model. Okay, so a variety of ways to come up with this 3. I think it's just easier to go, hey, how many betas, how many coefficients are we testing? 1, 2, 3, boom, done, easy, simple, right? Some people like to go 7 minus 4, ooh, 3, oh, yay! And if you're one of those people and that makes you happy, go for it. Okay, both get you to the same 3. The denominator degrees of freedom are the denominator degrees of freedom for the full model, based off the full model. Okay, so n minus p minus 1. P is the number of predictors, number of slopes in the full model. Okay, so n minus p minus 1, 38. And you can typically find that on the output. Okay. So now we go into the formulas. And the first formula is, when you're doing it by hand, the first formula is the easiest one to base your calculations from. Right? I remember we were talking about R squared adjusted, and we had R squared adjusted formulas that worked better if we were doing it calculations by hand with the calculator versus calculations on Excel where we were cell referencing. Same kind of idea here with the partial F statistic. Right? There are the main one at the top there. That's the one that's easiest to do when you're cranking these things out and doing the calculations by hand. And the other two are great if you're doing cell referencing. So on an exam, often we're doing these by hand, and the first formula is the most convenient to us because if we make a mistake and miss a number, the consequences are mild but not severe. You do that with the other two, you miss a number in a whole slew of 9 digits, the consequences are severe. Okay. But they can be very easy to do when you can cell reference on Excel. So for instance, in the lab, tend to focus in on one of the bottom two. When we're doing this by hand in the lecture, we'll tend towards the top one. Now, one thing to really zero in here is that R squared is not the R squared adjusted. No, it is not. It is the R squared, just plain old R squared. Okay? No little adjustment factors in there. Nothing like that. It's very important to keep track of. Nothing special as far as those R squareds. Old-fashioned R squared, and that's it. End of story. Okay. So now we've got our F stat all set out. We also can find p-values, and we'll find p-values via Excel. Okay, so we have I guess a little bit of it's a nice thing to be able to use Excel on an exam where possible, or to use Excel when you're doing these calculations, because you get the F stat tables. They're a little bit clunky to work with, and they're not the most pleasant things to play around with. So we're very, very happy whenever we can use Excel in these particular calculations. We can have a f.dist or fdist. Fdist is the legacy one. F.dist is the current one. F.dist.2t is also one that's going to be very important to us, and we'll talk a bit about that in a sec. Okay, so we get the p-value, and we are going to compare it to alpha in the usual way. Okay, so let's now look at those results. So we will find the F stat, and our F stat in our case will be the R squared from the full model minus R squared from the reduced model, and that'll be in brackets, divided by 3. 1, 2, 3, or as the count would say, 1 eliminated variable, 2 eliminated variables, ha 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 ha, oh, 3 eliminated variables. Okay, and R squared full, 1 minus R squared full, and divided by n minus p minus 1, which we had earlier to be 38. Okay, so now we just need to know what those R squared values are. So let's go back and look at our output again. So R squared for the full model, and let's just do it to four decimal spots. Anything more is clunky. Anything less could result in us over rounding. So I highly recommend no less than 4. Okay, don't do 2. 2 is just going to invite all sorts of tricky problems, especially if it's anywhere close to the edge. It can throw you over one edge or the other. And by edge, I mean close to either rejecting or not rejecting H0. So we want to get a few decimal spots in there, but we don't want to get too goofy because that's just a lot of work. And the other one, reduce 7.7118. And that's divided by 3. And divided by 1 minus 0.8169. And that's divided by 38. I recommend doing the numerator separate from the denominator, just so there's no order of operations, craziness going on. You hate to make a silly mistake. Anyway, you get about 7.275, give or take. Don't get into too much of a panic if you're out by a little bit on the thousands place. If you're much lower than 7.2, much higher than 7.3, then we can start to get concerned. Now, every F stat has a numerator degrees of freedom, right, in the numerator, which is 3 in this case. Sorry. And a denominator degrees of freedom, which is 38. Okay. So standard fare for us, standard representation of our F statistic. Fourth step, p-value. Now with the p-value, we get to drift over and have ourselves an Excel moment. Right? Bring in the Excel. It's Excel, it's here. Okay, so big deliverable for Excel, F. Oops, let's go equals to F dot dist dot RT. Okay, saves ourselves a little bit of trouble. I know Excel did the updates. It got all this dot stuff in there, and that's from R. But this dot RT thing, very convenient. The F stat is a right tail. It's a right tail test. So notice how it's not a two-tailed test. It's a one-tailed test just by the structure. Now you see some arguments come up there. We've got 7.275. That's our test statistic itself. And then you can kind of see that it asks for the numerator and denominator degrees of freedom. So I give it to that, 3,38. Close those old brackets and count to 3. 1, 2, 3, and magic! And kaboom. Kaboom, kaboom. Okay, so you want more decimal spots, just make the cell bigger. Don't want so much, make the cell smaller. It's okay. You could also make the cell bigger and smaller over here as well. Okay, so roughly our p-value is equal to 0.0000568. Pretty doggone low, right? Now the usual rules apply, right? Apply the usual decision rule, of which you know and you've come to love. P is less than or equal to alpha. Therefore, reject H0. Conclusion, at least one of the slopes is not equal to 0. Functionally, what does that mean? We want the dummies. Don't write it like this, though. Right? Yes, at least one of those slopes is not equal to 0. The dummy variables matter. Don't write it this way. But at least one of those variables is not equal to 0. And that is the F-test. That seals up, that is our F-test. Boom, beginning to end to done, right? Very straightforward. Oh, sorry. Bye-bye, Excel. And very powerful, though. Very powerful. Gives us a lot of flexibility. Now, we are not bound to test only dummy variables with this partial F. It works on any selection of variables, any selection of coefficients. Okay, whether we decided to take out the two advertising coefficients, the one with advertising t minus 1 and advertising t, those are quantitative variables. We could remove those. They're x4 and x5, and take them out. See if they significantly contribute to the model. Looks like the quarterly dummies do significantly contribute to the model. That's awesome. We're going to keep them in there. And there's the formula again, summary, calculation. Just going about it a different way in case you want to see it, not with the R squareds. Shows you that you get the same F stat. There's a critical value approach. We don't focus in on it. That's a little bit kicking it old school. You can find this F value by using this F critical value by using the F dot inv dot rt function, but it's not immediately important to us. Okay, so we can kind of see that, hey, yes, there's our p-value, which we already know what it is, and use of the 3 dummy variables significantly improves our ability to predict monthly sales of ceiling fans. That's the nice way. Colloquial way is, we want dummies, we want dummies. Right? Okay. And so there's your partial F test. Very nice. Little quick summary here. Multicollinearities, remember, that's when those independent variables are related to us. Really makes a mess of our regression coefficients. Screws around with the variances and the standard error of those coefficients such that perhaps we are not rejecting HO where we should be, i.e. we're saying that a variable or a coefficient is not significant when in fact it is. Very problematic. We have 2 ways to identify that: correlation coefficients, variance inflation factors. Partial F, right? We get to use to test more than one, but not all the variables. And again, it's nothing special about the ones we take out. Usually there's a reason that they're bunched because we're testing a question that they're common to, but it's not restricted just to that. We have a formula. When we're doing this by hand, looking at you lecture and midterms and stuff like that, the F stat with the R squareds in it's the easiest. If you're working on your project, doesn't matter. You may find that just cell referencing the SSEs or the SSRs are more convenient to you. That's up to you. As we saw earlier, get the same answers, so it doesn't matter. Whichever you find convenient. We kind of like to use, we want to use the Excel to find the p-value wherever possible, because the tables for the F-stats, they're like 3-dimensional tables. So it's sort of like playing 3-dimensional chess. It can get a little bit messy, a little bit clunky, especially when the values fall between 2 pages. And then, it just gets trickier. But we have Excel open to us, so not a worry of ours.